Uh, so now after we finish defining surface integral and infinitesimal area and the surface integral of a vector field, now we want to think if we can have something like Green's theorem but to 3 dimensions. And this will be the topic of sections 15.7 and 15.8. But I will start by section 15.8 because it's just give me the correspondence of the flux integral that we just calculated in 15.6 and related to the flux integral that we did in 2 dimensions with Green's theorem. Okay. So recall, so in 2D, I had C parameterized by R of T, parameterized by R of T, A between T between A and B, and I had ds is equal absolute value of V of T dt, and let's say F, and then we say, okay, then we said if C is closed, smooth curve enclosing R, so we had this C, okay, and where here I remember V of T was R dr dt, and this is R, and F equal M and P, so this is Green's theorem normal form. M and P, okay, nice, let's say having nice derivatives, well having, okay, let's write it, having continuous derivative in an open domain containing R, and C should be simple, okay, no self-intersection. Then the integral over the closed curve C f dot n d sigma ds is, which was equal integral of m dy minus n dx, is how we used to calculate directly, okay, which is my prime minus n x prime. This is equal by Green's theorem, so that's what Green's theorem tells me, the double integral over r of mx plus ny dA. Okay. Now the question is, what if I have S, a closed surface? How do can I use Green's theorem? I mean, is there a way to state Green's theorem in 3 dimensions? And the answer is yes, and this was the topic of 15.8. So 15.8, divergence. Theorem. So definition, given F equal Mi plus Nj plus Pk, the divergence of F is, remember in 2 dimensions it was mx plus ny, but in 3 dimensions is divergence of F, this is the notation, is the derivative of m with respect to x, the derivative of n with respect to y, plus the derivative of p with respect to z. Now as an example, let f of x, y, z equal x, y, e to the z. What is the divergence of f? X, y, e to the z, sorry, y, e to the x, and z squared plus x. The divergence of f is the derivative of the m component with respect to x, so this is y, e to the z, plus the derivative of this with respect to x, plus y, e to the x, plus the derivative of this with respect to z, plus 2z. And this gives me the divergence of f. Remember, the divergence of f is a function, it's not a vector, it's a scalar function. Now the theorem, which is the divergence theorem. Or what says normal form of Green's theorem in 3 dimensions, says the following: let f equal m, let's start with the surface. Okay. Let S be a piecewise smooth oriented closed surface. So this is a surface S. Okay, S. Enclosing a solid D. So what is inside is called D. Okay. Let F be, well, F equal M and P be, well, such that M and P have continuous first order partial derivatives in a domain containing S. So this is, I need some room in an open domain containing X. Then the outward flux, remember in the Green's theorem you have also F dot n. What was n, if you remember correctly? It was if the, since the surface oriented anti-clockwise, it was the outward. So same here. I consider I have two normal, either outward or inward. I choose the orientation that gives me an outward unit normal. Then the outward flux is double integral over S of F dot n d sigma. Again, this is outward, which means away from the, I mean, it's a surface, okay, closed surface. So it's pointing outward, outside, toward outside the surface. This is equal, I can go inside now, but inside is a three-dimensional body. So this is, what would you call the body? Sorry. Okay, I'm having trouble with solid D, size of body, divergence of F dV. So the surface integral, I can relate it to a triple integral, which we learn how to do in Math 201. So what is this saying? This is saying flux equal divergence times volume. So the divergence of F, so this is a theorem, corresponds to the flux density, same as in two dimension. So assume you have a balloon, okay, and the balloon is intact, like it's neither going, the volume is neither increasing nor decreasing, but the volume has some gas, and the gas is applied some force on the boundary of your balloon surface. Since it's neither going larger or smaller, then we say that the divergence of the vector field what is the vector field in this case? It is the force that is applied by the gas that is inside the balloon. So the divergence of this vector field will be equal to 0. So this is a divergence what measures. It measures somehow the outgoingness of my vector field. Now let's say we heat the gas inside my balloon, and this will make the this will make the gas particle moves faster. When the gas particle moves faster, the volume of the balloon will increase. So the balloon will inflate. So this means that the divergence of this vector field will be positive. Now, if after some time the gas returns to its normal temperature, this means that the gas will move slower, and then the balloon will deflate. Its volume will decrease. Then we say that the divergence of this vector field is negative. Okay, this is the significance of the divergence. Now, example, calculate the outward flux of F, which is equal x cube I plus y cube j plus z cube k across the unit sphere x squared plus y squared plus z squared equal to 1. Now the long method, so this is a sphere, it's a closed surface. The long method is to use 15.6 using the definition. Use the definition. In this case, what is n, by the way? This is a sphere, remember it's outward the unit normal. So n is x, y, z over the square root of x squared plus y squared plus z squared, but this is a sphere of radius 1. So this is x, y, z. What is f is x cubed, y cubed, z cubed. And then the flux, which is double integral of f dotted with n d sigma, this is equal to double integral over s of x4 plus y4 plus z4 d sigma. And this is equal double integral over s. Now now you have to parameterize. So now you have parameterize using spherical coordinate, maybe spherical coordinates, and will take you a lot of calculation. Now method 2 is using the divergence theorem. Now how do I use the divergence theorem? Then you have S a smooth, closed, oriented surface, and then you have F is x cubed, y cubed, z cubed. So I have M is x cubed, N is y cubed, and P is z cubed. Have continuous partial derivative everywhere. Have continuous partial derivatives. Then, by the divergence theorem, the double integral over S of f dotted with n d sigma is a triple integral over d of divergence of f dv. Now what is d? So you have a sphere here. This is S, and then d is what is inside. So this will be double integral, triple integral. What is inside is x squared plus y squared plus z squared, smaller, equal than 1. Then what's the divergence of f? Is the derivative of m with respect to x, 3x squared, plus the derivative of n with respect to y, 3y squared, plus the derivative of z with respect to z. So this is dv. But now how do I calculate this triple integral? Well, you have x squared plus y squared plus z squared, and you have a sphere. So this should scream spherical coordinate. So this is equal integral 3 x squared plus y squared plus z squared is rho squared. dv is rho squared sine phi d rho d phi d theta. Remember, this is a Jacobian. Now my rho is between 0 and 1. This is my sphere. My phi is the angle with the z axis. This is between 0 and pi. And my theta is between 0 and 2 pi. So this is equal integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to 1 of 3 rho 4 sine phi d rho d phi d theta. Again, I have a product of function depends each on one of the variables, like something depends on rho. Sorry, what's this? Oops. Times something depending on phi times a constant. You don't have dependence on theta. And all the coordinates are rectangular. So, you can first integrate respect to rho, and then the answer integrate respect to phi, and then the answer in theta. Or you can do this directly. This is 0 to pi times 1 d theta times 0 to pi sine phi d phi times 0 to 1 rho 4 d rho. And I have a 3. So this will be equal 3 times 2 pi times, what's the derivative of sine phi? It's integral of sine phi is minus cosine phi between 0 and pi times rho 5 over 5 between 0 and 1. And this will be 6 pi times 2 times 1 over 5. 0 to 1. Sorry. Yes, so this is 12 pi over 5. Okay. Now let's do an exam question. So example, usually done in the recitation, sometimes. Okay. Okay. I have, let S be the paraboloid given by z equal x squared plus y squared, and z is between 0 and 4. So this is a paraboloid oriented with unit normal pointing away from the z-axis. So this is n, and let f be equal xi plus yj minus 2zk. Okay. Now question 1, well, it's one question. Calculate double integral over s of f dotted with n d sigma. First part using the definition, and 2 using the divergence theorem. The thing is, what's strange that the question is asking using the divergence theorem, let's say part A, part B, is that the paraboloid is not a closed surface. Okay, the paraboloid is a surface, but I mean the disk here is not, the disk that here is not closed. So you cannot say that this surface is a closed surface. So you cannot apply the divergence theorem on S. So we'll see what question B really means. Let's start by calculating explicitly, and this will a good practice. Okay. And okay, I'm changing something. So okay. So part A. I have S is given explicitly. So I want to calculate using definition by z equal x squared plus y squared. But where is my x squared plus y squared? So if this is 4, then I see the shadow here. So I will write z equal f of xy equal x squared plus y squared. And what's the shadow with x squared plus y squared is more equal than 4? I take the shadow on the xy plane. Okay. Then the unit normal, okay, well then the sigma is equal to square root of 1 plus fx squared plus fy squared dx dy, which is equal to square root of 1 plus 4x squared plus 4y squared dx dy. Because what is fx? And scratch here. Fx is 2x, fy is 2y. Okay. This is the sigma. Now I need to find n. So what is n? I have two choices. Either minus fx minus fy comma 1 over the square root of 1 plus fx squared plus fy squared, or fx fy minus 1 over the square root of 1 plus fx squared plus fy squared. The first one is minus 2x minus 2y comma 1 over the square root of 1 plus 4x squared plus 4y squared, or 2x 2y comma minus 1 over the square root of 1 plus 4x squared plus 4y squared. Now I go back and look here, n is pointing downward. So from the figure, n is equal minus 2x minus 2y comma 1 over the square root of 1 plus 4x squared plus 4y squared. Then now I need to calculate the double integral over s of f dotted with n d sigma. The double integral over s, remember what is f, is xy minus 2z dotted minus 2x minus 2y comma 1 over the square root of 1 plus 4x squared plus 4y squared d sigma. And this is equal, well, you go now to the, now this is equal integral. Now I go to r, so this is x squared plus y. Well, before this, what is z here? I'm on my surface. So this is xy minus 2z. Okay, what I'm trying to tell you. Now I have to go to, this is the surface integral. Now I have to calculate surface integral. Now I'm on s, okay? Since I'm on s, I know that z, so on s is given by z equal x squared plus y squared, correct? So when you calculate this double integral over s, this is what? This is minus 2x squared minus 2y squared minus 2z, I'm doing the dot product, over the square root of 1 plus 4x squared plus 4y squared d sigma. Now I have to go and replace z by what is. So this is s minus 2x squared. Wait, we chose n. I'm very sorry about this. N is pointing downward. So n is this choice. So it's 2x, 2y minus 1. 2x, 2y minus 1. Sorry for this mistake, but I don't want to redo the video. So this is 2x squared, 2y squared plus 2z squared. So this is 2x squared plus 2y squared. Now z is x squared plus y squared plus 2x squared plus 2y squared over the square root of 1 plus 4x squared plus 4y squared d sigma. This is double integral over s of 4x squared plus 4y squared over the square root of 1 plus 4x squared plus 4y squared d sigma. Now I go to r, and this is equal double integral over r. What is r now? It's x squared plus y squared is more equal than 4. Remember? Of 4x squared plus 4y squared, because when r is the shadow on the xy plane, this is r. Into the square root of 1 plus 4x squared plus 4y squared. The sigma is square root of 1 plus 4x squared plus 4y squared dx dy. So this is double integral x squared plus y squared is more equal than 4 of 4x squared plus 4y squared dx dy. And now use polar coordinate. This is 0 to 2, 0 to 2 pi. I have r dr d theta, and I have 4r squared. So this is 0 to 2 pi d theta times 0 to 2 4r cubed dr, and this is 2 pi times r4 between 0 and 2, and this is 32 pi. Okay. Now method 2. Now the question is to use the divergence theorem, and I have to use the divergence theorem on the surface. So this is n, this is s. But s is not a closed surface. How do I make it a closed surface? By closing the unit disk, correct? Then s union s1 will be, well, let's call this s tilde. S union s tilde will be a closed surface, okay? So let s tilde be the surface x squared plus y squared, this is 4, remember? X squared plus y squared is more equal than 4, z equal to 4. Then s union s tilde, which I will call it s1, is a closed surface. And f which is equal xy minus 2z has the component of f, and well, f is this, so m equal x, n equal y, p equal minus 2z have continuous partial derivatives of order 1. Then, by the divergence theorem, the surface integral of S union S tilde of f dotted n d sigma is equal to triple integral over d of divergence of f dv. Now what is d? So I have this surface now. D is what is inside. Okay, it is the whole thing that is inside my surface. Now what is divergence of v? So double integral of S union S tilde f dot n d sigma. What is the question? Is to calculate the surface integral over S. Okay, but the question is to use divergence theorem, so I have to close my surface. So this is triple integral over d. Divergence of f is the derivative of n with respect to x, which is 1, plus the derivative of n with respect to y, which is 1, minus 2 dv, and this is equal to 0. Good. Therefore, I have 0 equal double integral over s. Now the integral over the union of surface, like inline integral d sigma, plus the double integral over s tilde of f dotted n d sigma. There's a double integral over s of f dotted n d sigma equal an integral of s tilde of f dot n d sigma. But what is s tilde? It is this unit disk. And since n was this way, if I move n continuously, my n here is upward, correct? So what is n on s tilde? This is double integral over s tilde of f dotted with k d sigma. Since f is what? Since f, well, is k, since the disk is on the plane z equal 4. So the unit normal is upward, so it's equal to k. And remember, f is equal x, y minus 2z. And this is double integral over s tilde of minus 2z. And you have here a minus. Yes, you have here a minus because the sum is 0. You have here a minus, you have here a minus d sigma. But on s tilde, because this is s tilde is on the plane z equal to 4, so z equal to 4. So this is equal double integral over s tilde of 8 d sigma, which is equal 8 double integral over s tilde d sigma, which is equal 8 pi. I mean, this is s tilde is x squared plus y squared is more or equal than 4. So 8 pi times 2 squared, which is equal to 32 pi. And we got the same answer. Okay, as expected. I mean, you should get the same answer. Otherwise, there's something wrong. Okay, I will stop here. Thank you.